Okay, today let's discuss section 8, Goursat theorem. The Goursat theorem is about the definition of analytic functions. So in this textbook, we require analyticity equal to continuous differentiability. Okay, so analyticity is continuous differentiability. The derivative is continuous. And the Goursat theorem says it is equal to differentiability. A complex function is differentiable, then it must be analytic. So that's what Goursat theorem says. Okay. Okay. So let G be an open set and let f from G to C be a differentiable function. Then f is analytic on G. Okay. Okay, so basically what do we miss? We only miss the continuity. So we're going to show we need only to show that f prime is continuous. Continuity is a local information, so we can say it is continuous on each open disk. Contained in G. So you only focus on the neighborhood, and that's enough for the continuity. And because we only discuss the open disk in G, so we will assume that G itself is an open disk. Itself is an open disk, okay? And now we have a differentiable function defined over an open disk. We show that f is analytic by Morera theorem. What is a Morera theorem? Morera theorem says, i.e., we show that the integral of f along whatever triangle is 0 for each triangular path. Triangular path is a triangle. Whatever triangular path inside the G. Okay, so that's what we're going to prove. we're going to prove this integral is always 0. And then by the Moreira theorem, FA will be analytic. And also keep in mind, G is open disk, F is differentiable. F is differentiable. Okay, so that's okay. So here's a statement of theorem, and that's what we are going to prove. And here's the setup of our proof. Okay, now let's continue. Let T be a triangular path. A, B, C, A. Let's label them. Well, it doesn't matter which orientation you select. You can select counterclockwise or clockwise. There's no difference. Now let's choose counterclockwise, because eventually we will show it is equal to 0. If you choose clockwise, you will get a negative sign. Negative 0 is still 0. So it's fine to select whatever orientation. So compatible. You cannot here you get the one thing, and then the final side you get opposite side, opposite direction. That's impossible, right? Okay, so we have this triangular path, and this triangular path together with inside like this triangle region. So let delta looks like a triangle. Let delta be the closed set formed by T and its inside. So T is just a boundary. T is the boundary, and delta means this region including the boundary. It's closed region. Okay, and then we know that the boundary of delta is equal to T. The boundary of delta is T. Okay. This is inside the open disk. This is inside a disk G. And then we use midpoint of each side to divide this triangle into 4 triangles. So use midpoints of the sides of delta to form 4 triangles, or whatever you let's just name them: delta 1, delta 2, delta 3, delta 4. This order is not the problem. So we have 4 triangles, triangle region. 4 triangles: delta 1, delta 4, inside delta. This large one is delta. And give the orientation compatible to the original, to the orientation of delta. So it means we're going to have here, then this one, and this one. They go this way, this way, this way, and sorry, yeah, this way, yes, correct. So this is a compatible orientation. Okay, so we have a large, technically it could be very tiny, but this part we consider as the large triangle delta. And then we divide the delta into 4 smaller triangles. Smaller triangle, let Tj be the boundary of delta j. So for this part, the smaller triangle is T1. Here is a T2. The smaller triangle is T2. This part is T3, T4, T5. Okay? And check here, when we talk about this triangle, the orientation of this side is this way. But when we talk about this delta 2, the orientation is the opposite. Be careful. The orientation I draw here are the orientation of delta 1, delta 3, and delta 4. They must be compatible with the original orientation. But the orientation inside the delta 2, its orientation is this way. It's still counterclockwise, is this way. Okay? So it's counterclockwise orientation for delta 2. So just be careful, the orientation is this way. Because of this orientation, we have the integral of f along t is equal to sigma j from 1 to 4, the integral of f along tj. Along this large t is equal to the integral of f along those 4 small triangles. And you see here, for the boundary, you have the same number, but for this 3 additional sides, for delta 1 you go up, for delta 2 you go down for the side. So that's the reason we choose the orientation delta 2 like this. They cancel the integral along the interior boundary. Okay, so that's very important. So that's why I want to emphasize, be careful about the orientation of delta 2. Okay, so you have a number as a sum of 4 numbers. 4 numbers, we can find one so that it has a largest absolute value. So you see, among these 4 numbers, there is a path called, we don't know which one, but let's just call it T sub 1. This T super 1. T sub j is T1, T2, T3, T4. They are the boundary. And among them, there's one we call it T super 1, such that the absolute value is greater than or equal to, is the largest one, is the largest absolute value. Okay? Largest absolute value. 4 numbers, of course, you can find a greatest number among 4 numbers. Right? Okay, then because we don't know what it is, what index you have here, we just call it T super 1. Okay, and from the simple geometry, we know that the length of Tj, each Tj, the length of each Tj, let's call it L of Tj, is the half of the length of T. This is half of this side, this is half of this side, this is half of the base, so it's always a half. And here we call it T, L of T, the length of T. Okay, so the length is half of it, so L of Tj is half of L of T. And the diameter of Tj is equal to half of the diameter of T. half of diameter of t. And by the triangle inequality, remember we have integral f along t is equal to the sigma integral of f along tj. By the triangle inequality, we'll move this up value into the sum. It's like this, and each of them is less than the integral along t super 1. Okay, so it's less than 4 times up's value of integral of f along t super 1. This t super 1 could be t1, t sub 1, t sub 2, or t sub 4. It doesn't matter. We just get this symbol notation. Okay, so we have, check here, we have one step. This is a one procedure. One procedure, we have this, and this inequality. Okay, so we have three quantitative relation. So proceed the same process. Now we have this t super 1. We are going to focus on this t super 1. Without loss of generality, let's assume, here we just assume the t super 1 is this, the left corner, delta 1. And what is the same process? The same process is this. You find the midpoint of 3 sides, you divide the region into 4 sub triangles, and here you will have delta 1 1, delta 1 2, delta 1 3, delta 1 4. You have 4 triangles, and among them there is a T2, so that T2 has a maximum absolute value among them. Okay, so proceed the same process on T1, we get T super 2 with what property? Let's check. First property, f integrate along T1 is less than or equal to 4 times f integrate along T2. This is one property. And the diameter of T1j, diameter T1j, you divide the T1 into 4 parts, is 1/2 of the diameter of T1. And T1j, this is the same thing. For 1, 2, 3, 4, they are all equal. So this one is actually equal to the diameter of T2. So let's just, T2 is one of them. So you just use a T2. And the length of T2 is equal to the length of each sub triangle. So they have the same length. It is equal to 1/2 of the length of T1. And of course, T2 is part of T1, triangle, that's my bad. Not T2 is part of T1. The corresponding delta is part of a corresponding delta 1. So this large one is delta, and some small triangle region is a part of it. Okay? So let's see, we have 1, 2, 3, 4. 4 conditions. We have 4 conditions. We can do this process for T1, and we can also do it for T2, T3, T4. So let's repeat this. process, we have, first, let's follow the order in the textbook. First, we get a sequence of triangles, smaller triangles. It's the first one. One is contained in the preceding one. And second, the integral over the nth level is less than or equal to 4 times the integral over the next level. We always pick up the triangle with the greatest ups value of integral. 3. The length is always half, not equal. It's not less than. It's half of length of Tn. You always divide it into 4 pieces. And 4, the diameter is also half of the diameter. Okay, so that's the 4 properties. The 4 properties. Okay, so every time you have a 4, so you get T1, you get 4. T2, you get actually 4 squared. So if we not use n, we use original t. So these inequalities imply, okay, that's 5. The original integral is less than or equal to 4 to n times ups value integral of f along the t super n. And the length of t super n is equal to 1/2 to nth power the length of t. And the diameter of t to n is 1/2 of 1/2 to n, the diameter of t. Diameter of t, diameter of delta, there's no difference. Okay? Okay, so these 3 are the corollary of the last 3 part. And the first one, delta 1 contained in delta 2, and they are closed, and the limit of the diameter of delta n approaches 0. This is a fixed number. You have 1/2 to nth power, so this limit is 0. Then by counter theorem, what is a counter theorem? Counter theorem means you have a chain of closed regions. You have a chain of closed regions. One is contained in the preceding one. If the diameter approaches 0, then the intersection is just 1 point. That's a counter theorem. So by the counter theorem, we get that the intersection of all these triangle regions is just a point. It's just 1 point. Okay? Need to lift my right? So this is counter theorem. Okay, now we focus at that point. We focus at this Z0. Remember, so far we only use the integral. We don't apply the differentiability. So given epsilon greater than 0, f is differentiable, has a derivative at z0. F has a derivative at z0. So there is a delta greater than 0. For epsilon, there is a delta such that for the open disk centered at z0 with a radius delta inside the G, and this fz minus fz0 over z minus z0 minus f prime of z0 is less than epsilon. That's by the definition of a derivative. Whenever you find a point z minus z0 less than dot. Okay, so this is just an application of a derivative. Okay, and we be careful here, this is not equal to 0, greater than 0. So we multiply this inequality by the opposite value of z minus z0. So equivalently, fz minus fz0 and minus f prime of z0 times z minus z0 is less than epsilon z minus z0. We just multiply this by this quantity. It's not equal to 0, so we can do it. And same thing where opposite value of z minus z0 is between 0 and the delta. Okay, so you see this is z0, this is delta. Because the diameter, n approaches infinity, the diameter of delta n is 0, and z0 belongs to all the delta n. So eventually, there's a delta n looks like this. Okay, so there is an n in the integer set such that the delta n belongs to the open disk centered at z0 with radius delta. Okay, so by Cauchy theorem, what is the Cauchy theorem? The integral of analytic function is over the closed contour is 0. Over closed path is 0. So what is the analytic function? Constant function is analytic function. Constant 1. And z is analytic function. So we just apply the Cauchy theorem for those two special functions. They are both 0. And Tn is the boundary of a delta n. Tn is the boundary of delta n. Okay? Okay, so just for these two special functions, let's not use f, let's use g. G is equal to 1, h of z is equal to z. They are analytic. Okay, now let's estimate the integral. We estimate the integral. The integral f. Let's see why it is equal to this one. we write it in a very, very fancy way, but technically this part is an analytic function. F z0 is constant, f prime z0 constant, z minus z0 is a linear function, it's analytic. So this whole part is analytic function, so its integral is 0. So this part disappears. So you still have fz, integral fz. So it's just a fancy way to write the original integral along tn. And then we can move this ups value into it and apply this inequality. So it's less than or equal to, first let's write this middle step. You first move this ups value inside of integral, and then you apply the triangle. You apply this inequality. So it's less than or equal to epsilon integral Tn z minus z0 dz. Z minus z0 dz. Okay. Right. Okay, let's continue. Z is on the boundary of this delta. Z is on the Z is on the triangle. Z0 is inside the triangle, so the distance is less than the diameter. So here, let me write it here. Z minus Z0 is going to be less than or equal to the diameter of Tn, or the diameter of delta, the same thing. These two things are the same. Okay, so it's less than or equal to epsilon, the diameter of Tn. When you put diameter of Tn, then you will integrate this constant along the triangle. So you get the length of the triangle. So this step is equality. This step is equality. Here's inequality. Okay, let's go back. In the collection of a property part, we know that the length of a Tn is equal to the 1/2 to n, the length of the original triangle, and the diameter of Tn is 1/2 to n, the diameter of the original triangle. Okay, so we are going to apply these two properties. So it is equal to epsilon. This is equality. Again, this is equality. You have 1/2 to n, 1/2 to n, so you have 1/4 to n. And then this is a diameter of T and the length of T. Remember, we start from a triangle. It is fixed. So this is a fixed number. This is a fixed number. Right? So they're fixed. And what did we prove? What did we prove? We proved, let's summarize. We just compute the ops value of f, the integral of ops value of f along Tn is less than or equal to epsilon 1/4 to n, the diameter of T, the length of T. So this is what we just computed. One more thing. In the collection part, we have this, the integral along the integral of f along the original T ops value is less than 4 to n times it. So the integral of f along the original T is less than or equal to 4 to n times the integral of f along the T super n. So you have 4 to n. And then you 4 to n times 1 over 4 to n, they cancel. So it's less than or equal to epsilon diameter t, the length of t. Diameter t, the length of t. This is a fixed number. Epsilon is a random, arbitrary. We have the integral of f, put up's value equal to 0. Put up's value with or without up's value is the same thing. 1 you get 0. So we proved that, or we computed that the integral of this differentiable function, check here, we only use differentiability. The integral of differentiable function is along any triangular path is 0. Then by Moreira theorem, it is equal to it is an analytic function. And in the okay, so that's the proof. In the whole part, technically we don't really use that the domain is an open disk. The only property we use for domain is open disk is that whenever I have a triangle, the region is totally inside this. The triangle region is all totally inside this domain. That's the only thing. So whenever you draw a triangle, 3 point is inside the region. So that's the property we use. Actually, we can assume G to be arbitrary convex set. Okay, so after Goursat's theorem, we can say that a complex function is analytic. You can say if it has continuous derivative, or you can just say if it is differentiable. The same thing. Okay, continuous differentiability is equivalent to differentiability. This is the same property. Okay, very good. Now we finish chapter 4 about the analytic functions, general introduction. And now let's talk about chapter 5. Chapter 5 is a singularity when it is not differentiable. Singularities. Singularities is a discussion about the bad point when it's not differentiable. So the first section, classification of singularities. Classification of singularities. Definition. A function f has an isolated singularity. Isolated singularity at z equal to a if there is an r greater than 0 such that r greater than 0 such that f is defined and analytic in the open disk without the center, but not in the whole open disk. Basically, it's analytic around A but not at A. Okay, so this is a isolated. So there's only one in its neighborhood. This is a unique bad point. Okay, the unique bad point. So that's the definition, isolated singularities. And the point A is called a removable singularity. A removable singularity if there is an analytic function G defined over the whole open disk such that G of Z is equal to F of Z for Z inside open disk but not equal to the center. Okay, so this is a removal. And isolated singularity. What is isolated singularity? Isolated singularity means it's good here, but not at the center. Okay, so we just want to study the singularity one by one. We don't want a convergent sequence with bad points. Removable just means technically we can fix this point. You see, we get an analytic function over the whole disk. This G is well defined over the whole disk. F coincides with G over this the annulus, the punctured disk. Then you can redefine F to be Fa is G of A. Then F becomes analytic. So that's a removable, like the removable discontinuity in our sense, right? So we can prove, this is an access, we can prove that sine of Z over Z has a removable singularity at Z equal to 0, because this one has a limit. Remember that from the calculus we know that sine Z over Z has a limit of 1 at 0. Okay, it's a removable. But 1 over Z, exponential function of 1 over Z have what's its word? Isolated, but not removable singularity. At Z equal to 0. Okay, so it has isolated but not removable. You can actually prove it. For example, this one is simple. This is the proof of this is simple. If it has removable singularity at Z equal to 0, for example, G analytic in the disk B01 gz equal to 1 over z. If z is not equal to 0, then the integral g of z dz along the boundary C1 is unit circle, then this integral will be 0 because it's analytic. Analytic then by the Cauchy theorem is 0, but we use a counterclockwise orientation. This is equal to 2 pi. That's impossible. That's impossible. By the winding number, you will see it's impossible to have a removable singularity. Yeah. So I tried to say something, but I don't remember. Okay, I tried to say that sine 1 over z. Sine 1 over z, let's check. Z is k pi. Z is k pi, yes. When z is k pi, 1 over k pi. When z is 1 over k pi, then sine 1 over z is sine 1 over k pi is sine k pi is 0. Okay, it is 0. Then we choose f of z as 1 over sine 1 over z. 1 over sine 1 over z. Then this means first z equal to 0 is singular. Z equal to 0 is singular. It's undefined at z0. And second, all these numbers, this is singular for k belongs to the integer set, and they converge to 1 over z. 1 over k times n converge to z0. So z0 is a non-singular, a non-isolated. 0 is a non-isolated singularity. We don't want to study this. Yeah, I tried to mention this part, so I just don't remember what I'm trying to say. Okay, so this argument is about the isolate property. So this is an example which has a non-isolated singularity 0. It's non-isolated singularity 0. We don't study this. We study a isolated singularity, and the first simple case is this removable singularity. Removable singularity. Okay, we stop here today, and next time we will prove a theorem which quickly help us to determine which what singular point is a removable singular point. Okay, we'll stop here. Thank you.